Alright, time for another DraftPhysics.com, debatephysics.com also. Video presentation. So still on the subject of the 1.4 square root of 2 free momentum energy thing. Okay, the idea that whenever you exchange between objects that have uneven masses, that is, you take energy that's in a bowling ball going 8 miles, an 8-pound bowling ball, and you put the energy into a 16-pound bowling ball, you have a problem that you're going to end up, in that case, making free energy, free momentum. So the 16-pound ball is going to end up having more momentum for some reason. And if we go the opposite way, and I take the energy that's in a 16-pound ball and I put it in an 8-pound ball, I'm going to lose half the energy, perhaps. I mean, in this case, this argument, half the momentum, okay, will be destroyed. So, doesn't sound right, on its face, that any experiment could destroy or create momentum. So, I just argue it's sort of a thing that has to be resolved. Now, we have discussed in the past an experiment where they make, okay, so just showing he's got a 1.4 result again, okay, for an experiment, 2 minutes worth of video, so it's, whatever, but we'll go back to that. So we'll just do the context first. Alright, so we have the classic Professor Lewin type experiment, okay, crashing light car, right? Yeah, I have to remember the experiment, it's been a while. Yeah, crashing light car into heavy car, okay. And so say we're going in with 100 momentum. What we end up with is a 2-mass car that leaves with 133, and we end up with 33 reflecting this way. Now in this new experiment, okay, the minus 33 thing isn't going to exist anymore. So we're not going to be able to say, oh look, we subtract the 33 and it's all okay. We conserve momentum in this direction. In this experiment, there is no conservation based on direction. So the whole direction theory becomes a little suspect, because what we're going to have in this case is something's going to come in with 100, alright, and in one example, okay, it's going to convert the 100 into 150 momentums, and they're going to be going in exactly the same direction. And in the other case, you're going to start with 100 momentums, and you're going to have, when you get done, okay, you're just going to have 50 going this way, the same direction. Now you can have it go the opposite direction if you like. You can choose which direction, because it is a pendulum. So you can have it either way. So when you start with a light thing and you put the energy into a heavy thing, twice as massive, you gain 50% momentum. And when you go the opposite way, you put the energy into the heavy thing, and then you put, have it go into the light thing, you end up losing minus 50% of the momentum is destroyed, okay, because there is no explanation provided, at least for a system where the energy could be going. There's no losses essentially in the system, because whatever this lost momentum is, this object will essentially just redo this experiment. So these two experiments are just inverting with each other, and so in one case you lose half the momentum, but yet the thing that had lost half its momentum will give it back, okay. In the next experiment, the momentum will go back into the object, and you'll start back at where you left off. So you're going to keep going circularly, where you lose half the momentum, the system has half the momentum, and then the system has 100% of the momentum again, and then it loses half the momentum, or vice versa. You could look at it depending on how you start, whether you start with the heavy object or the light object. You can say you started with the deficit and you gained the free 50%, and essentially, like I said, it is free. So anytime I go from a light object to a heavy object, I can make 50% free momentum. That's with a 2 mass. Now if I make it a 3 mass, maybe it can be 100%. Maybe it's 75. You have to test these things. So we'll have to see what the 3 mass does and see if we can get all the way up to 100% increase. But anyway, I have my doubts, okay, that this is going to continue to be a real theme, and that the argument is that something else is to blame for the results. Now, so the coupled oscillator, I figure, was a pretty good experiment, just because in theory, okay, it's doing something fairly simple. The idea, as I explained it, is that you have two pendulums, and what you're really doing is just creating a very subtle system between them, that when this one moves, with each farthest move it makes, it does a little tug on this one. So it pulls on it a little bit, gives it a little energy. So this one loses a little, this one gains a little. This one loses a little, this one gains a little. This one loses a little, this one gains a little. And the idea is all the energy eventually ends up over here that started over here. And there isn't any in here. Now, this bar setup is a little different than what I suggested. I suggested as minimal a connection between the two as possible. He doesn't have a steel bar, but he has a rubber band that's very taut. So it never goes loose as far as I can tell. He doesn't, we get 2 minutes of video and he hand holds the camera, so you can't do frame rate, you can't do anything. He doesn't have the camera even stationary to look at the experiment, and there's no angles, of course, so you can't see it from any other angle. So you can't see what's happening here when something's happening here. So I just can't be sure, that if you make the coupling too rigid, and especially if you make it very rigid in the sense that you have this scenario where the pendulums aren't even swinging independently, that this one is tied essentially to this one, and they're always compressing each other. They're always pulling each other in. So there's always pressure on them. So if you did swing this one out, you would invariably swing this rubber band this way. So you'd have extra energy in the rubber band. Okay, no doubt about it. Stored energy. And that's what you want to try to avoid, in my opinion. You want a coupled oscillator where the pendulum is independent when it stops. So when it stops, it's a straight line, not any kind of crooked line. So you want the pendulum to stop, there being no energy in its system at all, guaranteeing that all the energy has to be in the contraction device and the other pendulum, that's moving. I mean, ideally, I would think that would be the logic of the experiment. So, but I can't say for sure. So that's a defect in my opinion. It's not what I did, let's put it that way. I kept trying to minimize this connection. So I made it, as light as possible, a system of little rubber bands, and the amount they expanded was never like super tight. They just made a little bit, like the rubber bands go up and they'd go down. Just the weight of the rubber bands was enough to convey the energy. So just the amount of gravitational pressure being put on the rubber bands was enough to convey the energy from one side to the other. Kind of. Making sure that it's a very little bit of energy transferred at a time, and that you can't have energy in both systems. That you can actually get all the energy into one side. But you always have to account for the fact that it's got to be something in this. But you're just saying if this is stationary, then this can't be very tense. It would be the argument. It can be a little bit up if this swings all the way out, but it can't be putting that much pressure. So it can't be accelerating it that much. Now, the argument is that it does really pull from the outside in. Okay, so that's the other thing you have to be aware of. That all of the transfer of energy happens pushing from the outside in. So when this one's oscillating, it starts to push on this one from the outside in. This rubber band stretches and it pushes this way. Now that unfortunately changes your gravitational maximum velocity point in a sense, right? This might not be where that acceleration or that push has maximized your velocity. So your maximum velocity might actually be here, you know, some point closer in, where you're actually now going against the gravity, but you're not going against it more than the fact that your acceleration from the rubber band's compression is pushing you more than this gravitational burden. So I guess the second test would be is to move the timing gates in and see if you get different maximum velocities. Just speculating on that being a problem. I mean, it seems a potential problem just because you're not really dropping it from this height, all right, essentially. So when it goes out and it's going to push this object, that means it's going to put stress on the rubber band, and the rubber band's going to want to push it back. So I'm just saying that is an extra acceleration. How much it affects the experiment, I don't really know. All right. Now the other problem I stated was it'd be best to have, since he's using timing gates, it'd be best to have two objects that are the same size. And even without them, it just makes it visually easier to track. So he says that's impossible. You know, I'm saying no, it's really not. You just have to think about it for a while. So I would argue that pill bottles are pretty standard size. So find two pill bottles that are the same size. You know, make a little bucket out of them, and then you can put any mass you want inside of them. You know, doesn't matter. I mean, I wouldn't put a fluid inside because fluids move too much. But, you know, put something that's not going to move too much. You know, if you have to, shove a little paper around it, stop it from moving. Try to get it sort of in the center of the object. But basically, that's all you need is two buckets that are the same size. Then they'll be passing through the timing gate at the same time. And I think that would be preferable. And if they spin, it won't matter to their profile size. Their size will be the same regardless of whether they spin a little. So it's a little better than putting a piece of cardboard in front of each of them, because you couldn't guarantee which way the cardboard turned. So you'd be better off with something, you know, that can't change its profile. No matter how much it spins, it's the same profile. Which leads to an issue. You know, there's always something, the way somebody does this experiment or films it or something. And there's a problem with his video, an angle thing that just doesn't look right. I mean, you have two, basically they're timing gates, right? And he's basically going to say, look, the two things are going to swing through the timing gate. Well, one of them, okay, I mean, I don't know really how to draw it. It looks canted, okay, like this. And the other one looks square, like this. Okay, so you got to wonder what that's. One of them looks tilted, okay, and the other one looks square. Like they don't line up this way and this way. I mean, we're presuming the pendulums are lined up, so the timing gate should line up also. It doesn't make sense that they wouldn't. So, you know, but who knows if this is a real thing or just a, you know, could be an optical illusion. I'll show you the video. Or it could be a real thing. Can't say. I guess if we find out that the results, if we find out that it changes the results, if he changes those timing gates, then we can assume that yes, this is always the same game that's going to be played. It is, they rig the experiment to come out their way. Okay, they do it numerous ways, they get different answers, and they just wait until they get the answer they like, and then they show that experiment. You know, and all you need to do is tilt the gate a little bit, and oh yeah, you can get the results you want. Especially in the second case, frankly, the case where the heavy mass provides the energy in, it really does look like when the energy is now in the lighter object, it does look like a hell of a lot more than 1.4. I mean, really, it's 0.4, you know, faster. It does look like more than 0.4 faster. But anyway, so we'll play the video. I'll make those last points. Just trying to think if there's anything else I can point out. So again, this goes back to, there's numerous experiments doing numerously weird things that just aren't consistent. So we have the other experiment where physicist Michael, you know, puts one masses on a spring, the same spring, right? He gets 100 and 100. Puts two masses on, okay, and gets twice the momentum. Gets 200 and 200, you know. So he gets 400 total momentum when he puts heavy objects on. So heavy objects seem to absorb energy so much better. And only 200 when the light objects are on. And then in this experiment, it's the inverse. The light thing isn't absorbing the energy well at all. You know, we're losing half the momentum. And the heavy thing absorbs it very well because we're gaining 50% more momentum. So again, so there's a lack of continuity. Like, how come it's, you know, how come energy goes into heavy things better here, and then energy goes into lighter things better in this new experiment with the coupled oscillator? I mean, it lacks consistency, let's just say. But we'll see where it goes. Again, if I have to do these experiments, I will. Blah 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 blah. Because I don't see where free momentum isn't a problem. Because I'm just saying, if you could do one experiment, make free momentum, then you can do it again and again and again, and that just doesn't make any sense. And it makes no sense that nobody would have capitalized on it in all these years. If you could actually double something's momentum. With a benign contraption attached, that nobody would have taken advantage of that by now. All right, so to the experiment and such. Should work. There's the result. Okay, so those are the results. This is the 2 mass starting with the energy. So this one I think does look rather dramatic. In terms of the motions, do seem, it seems like a lot of motion. Okay, so I'm going to blow this up just to show what I don't like visually. And, it just doesn't look right to me. So you can see that this looks pretty square, and this does not. Okay, they're not lined up parallel to each other, which doesn't make any sense. They don't seem parallel with the flow of the 2 objects, and this one appears to be tilted. It appears that that's what's wrong. It's tilted forward. So it's not just that it's out of place. That is, these 2 chords are not in alignment. It's that it's tilted too. It's tilted. You can see that, right? It's tilted. I can see it. So it just doesn't look right. So maybe that's just the camera's fucked up. Maybe it's a really weird camera and it distorts images a lot. I don't know. It just don't look good. And it would make a difference, frankly. If the timing gate is tilted and the object's going through this way, it does change its profile definitely this way. It just definitely makes it look longer, but any distance change makes an object look bigger. So if something crosses my path here, it's going to look bigger than if it's out here. So a difference of an inch or 2 in terms of where you're swinging to the sensor, right? The sensor is seeing the object. The sensor's just like you looking at something. It's big if it's close to the sensor, right? This camera, okay, sorry. And then the further away, right, it's getting smaller and smaller by the inverse square law, actually. So its capacity to turn on and off the sensor changes depending on how close or far away it is. So that's something that sort of has to be regularized. I think you have to account for that. I don't, I'm like I said, I can't say it means anything in this experiment. Now the fact is, okay, they have this little, I don't know if you can see it, there's a little screw thing here. So you're supposed to attach these, or you can attach them to a steel rod or some kind of object to suspend them. So I think that's all those are, is just little screws you tighten. And so you can have it very consistent and parallel. You can keep the 2 gates very parallel, very straight, very 90-degree angly. And he hasn't chosen to do that for whatever reason, to take advantage of that. But yeah, I think it's an issue. I don't know how much of one it is, and frankly, I don't know if it's going to change his perfect results enough. But I mean, 50% is a lot of momentum. So I'm just saying, it seems, it seems a lot of momentum to account for. But again, you don't need much of a change in these numbers. It is all kind of, 20% difference here makes a 60% difference in the answer kind of thing. So, and again, we can't see the whole experiment, so we can't see what his big rubber band at the top is exactly doing. Is it going back and forth too as the experiment takes place? What's it doing? How much motion does it have in it? How much stretch does it have in it? These are all, who knows, unanswered questions. So maybe he can do more experiments, show it from more better angles, and straighten certain little things like that. Maybe even try, again, to regularize the experiment so the two objects are the same size. Now he accounts for that. He says the larger object is 2.5 centimeters and the small one is 2. Just looking at it, again, you're saying, it almost looks like the bigger one is 3 centimeters, but who knows? It looks like it doesn't mean anything. So we didn't see that measurement, but yeah, okay. So I'm just saying, so then you have to obviously divide both numbers by, 1 by 2 and 1 by 2.5 to get your answers. And he seems to have done all that correctly, so I'm not saying he made a math mistake. But it would just be better not to have to worry about making compensations for the size of the thing you're putting through. I guess you could also argue that the smaller object, it would make a bigger difference. The bigger the object, the less this feature of being in front of the camera thing matters. So the smaller it is, the more this difference is going to matter for the amount of distance he's moving it. When you're moving 2 inches, if I can make this thing thinner and thinner, that 2 inches becomes more and more important in terms of how much the size changes. If the bigger the thing is, the less difference it is, okay, in terms of how much you change its profile. So those are all things to wonder about. It just doesn't look, it looks like one side is swinging through a different part of the timing gate than the other one is, but it's just hard to say that that would matter, and that he did it on purpose or any of that. But it just don't look very good. I mean, this, it really just looks obviously different. I'm just saying, if you look at this gate and you say, okay, this is what it's supposed to look like, this one doesn't look like this one. It's just a fact. They don't, it doesn't look right. It doesn't look straight. I mean, everything else here looks pretty straight. This line's pretty straight. These gates are not straight to this line. So if I use this line as a straight line, these gates aren't straight to that line. Okay, so maybe they're uneven to the way the thing swings, so then you just turn the whole thing this way. But then if you swing it this way, then they're not parallel lines anymore. These two things aren't parallel. Both of them are twisted in this direction. So both of them are looking, at an angle this way. You want them parallel, So anyway, so a lot of things to wonder about there. Just a lot of little issues. Okay, maybe some of them are important, maybe not. I'm just saying, I'm not convinced at this stage yet, okay, that this is a real thing. The free momentum thing is a real thing, because it just doesn't make any sense. I'm sorry, free momentum just doesn't make any sense. Alright, so till then, are some inability to get energy from that somehow the momentum isn't the truth, and that heavy things with less momentum, no, with more momentum, heavy things with more momentum that you can't convert, that you can't take the energy from a heavy thing and put in a light thing without losing energy, and you can't put the energy from a light thing into a heavy thing without gaining momentum. Just doesn't make any sense. But anyway, we'll see. So let's play some of this and call it a video. Might as well go back to the beginning. It doesn't say anything, which is nice. So it's just the experiment. So he's pulling the weight over. Now we don't see the big rubber band. We don't know where the whole rubber band is moving. So the two wires are sitting here. We don't know if they're both now canted at the rubber band. That is, they're not straight lines from where they're connected. The whole system is being twisted by the rubber band that's making constant contact between both sides. Alright, but we can't see any of that. Now you're going to get a little bit of movement in this because that's sort of inevitable. So yes, it goes a little bit in that direction because no matter what kind of system you use, you have to put a little bit of pressure on the other object. You can't avoid some pressure. Alright, so it begins. And obviously this one starts moving a little. Okay, the little one. And it hasn't been pushed the other way yet. So the key point would be in that first swing, it hasn't gone outside yet, which means so it can't be accelerated. It hadn't been accelerated yet from the outside pressure, beyond the pressure of him holding it. So it's going through this. The rubber band's now relaxed because the two things are closer to each other. So it can't be putting any pressure on it that way. So there it moves a little bit forward. Now that's what's left over from when he started it. So that's how long it takes the energy to get to the other side. So that push out isn't being created by anything except the relaxation of the rubber band. Like I said, see, if the rubber band's always in contact, now he's relaxing the contact. And so now the thing's going to its real neutral position. That is, that pendulum is now really lining up with where it wants to be. Where it's, see, if he's got the rubber band attached and is forcing the two pendulums in, you can see that if one swings this way, then this one can go to its natural straight line position. So again, back to my point, I did the experiment so you don't change those straight lines. The coupling doesn't change the straight lines of the pendulum. So the two things are independent of each other. They're not tied to each other. We're playing, but nothing's playing. Okay. He's showing us the initial velocity in. Okay. Alright, so the energy is about halfway transferred now, and you can see it's really, really quite a wide swing. It looks like more than 0.4, right? I mean, that's pretty aggressive. That looks like more than 0.4. So there, this one stops, and now this one has all the motion. And it certainly looks like more than 0.4, the velocity, but you know, that's just looking at it. So I would have preferred if he didn't edit these videos, and I prefer if he didn't hand hold the camera and blah 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 blah. I mean, we can read the timing gate. We don't need him to stop the video, edit it, you know, put an edit mark in the video. Yeah, don't need any of that. Okay, so that was this swing going this way, the same direction as it initiated, was the swing that he counted as the low one. So that's the other thing. We really should have the direction. You know, for the lowest, the quickest speed he gets, he should just put an arrow over it just to account for which way was it swinging when you got that lowest reading. Now you can see that the lighter one is going through both sides of the timing gate. It goes through one way, and then back the other way, and it doesn't seem to make any difference to the time. Now it doesn't seem to. You know, I mean, it's either going up or down, but it's not creating a huge differential. So maybe the fact that these timing gates aren't even doesn't matter. But it sure doesn't look right. And that sure looks like more than 0.4, but whatever. So he only does the experiment once, you know, which is okay, but you know. That stopped. That's going its peak oscillation. So the thing is, we'd prefer to be able to measure the heights, because the heights really are telling how much work it's doing against gravity. So again, the velocities could be deceptive, because the point where it reaches its maximum velocity might not be the bottom of the pendulum, because you are adding energy. When you force energy in, then your point of peak velocity isn't have anything to do with gravity. It has to do with when you got all of that energy in, when the rubber band stopped pulling. And if the rubber band if the rubber band is still pulling when you're here, at the bottom, if it's still pulling this way, then your peak acceleration is going to be somewhere else. That's a problem. So it might be better just to do the test with both timers on the same object, and just get your velocity numbers from 2 points on either side of that center, just to make sure one swing isn't stronger than the other swing. That would be a good test for that. I mean, even the fact that he kept switching, from one side to the other, that's nice for continuity or compressing the video. But if the timer can just keep rolling, and just keep telling you the number, then why not just do the whole cycle for the one mass and then do the whole cycle for the two mass on the other side, and just try to get the same energy in, something close to the same. That might be even more interesting as data. Alright, so this is what he shows as the conclusion. Now, he should write right here, okay, the momentum going in, 100. Momentum coming out, 50. No. I mean, out of the second side. And then momentum going in, 50. Momentum coming out, 100. Then 100 going in and only 50 coming out. And then 50 going in and 100 coming out. But he didn't show that. But that's the implication of these numbers. The implication of these numbers is that the momentum number went from you lost 50% of the momentum, you gained 50% of the momentum. You lost 50%, you gained 50%. You lost 50%, you gained 50%. Somehow the oscillator has more momentum on one side than the other side. And that's the part that is pretty hard to make any sense out of. But I think it might have to do, again, the first target of inquiry would be how big is that rubber band and how constricted are the two pendulums by it. And if you're pulling the two pendulums into each other with it, then that's a defect, in my opinion. That's where the extra momentum might be. So anyway, till the next time, that's probably enough. We'll see what else he does, blah, 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 blah. So it continues. The argument continues. This is not quite clear and decisive evidence, in this form anyway. So, till the next time.